All right. So what did we talk about last time? We talked about applications of integration. And there's a lot of applications of integration. We can find the cumulative change. If we know how fast something is changing, if we have a rate, and we want to know some total, well, we just integrate the rate between the two endpoints. That gives us the total. There's area, which obviously integration seems tailor-made for area. Because the way we think about integration is we think of it as Riemann sums. And the way we think about Riemann sums is splitting up into small pieces, small areas, and adding them up. So we can do area. What else can we do? We can use things such as if we know the density and we want to find some total. So maybe we have a population density, people per mile square. Maybe we have a density in terms of weight. We want to find the total weight. And we can find volumes. And we have volumes of cross-sections. So before we jump into our volumes, let me just remind you a few other things. We have all these great antiderivatives, which are the key for integration. These, you should all know these. Even though they are written on your final equation sheet, you should still all know them. Because just because I give you the equations does not mean that the next professor will. And I've gone in trouble before with students who said, "Oh, Professor Butler, you were too nice. You gave us too many equations. We never memorized these things." And then I got killed in the next class. So you should still memorize these. Okay, but we talked about those a lot, so I don't want to go over them again. One other application, of course, of integration is finding the average value. Now, the way we think about average value is you add up your numbers and you divide it by how many numbers there are. It's kind of the same concept, but kind of a little bit different because we think of our function as defined from the interval from a to b, and there's just infinitely many points, so we can't just add them all up. But integration is essentially just adding them up. So we think of the integration as adding up all the numbers, and then we just have to divide by the length. So this is the average value of the function. Now, geometrically, another way to think about average value is if I have some curve between A and B, then the average value is simply the height of a rectangle that you would have to make with the same length between A and B so that the area of this rectangle exactly matches the area underneath the curve. So geometrically, that's how you can think of average value. And average is another way to say mean, so of course there's a mean value theorem, which is another way to think of it as an average value theorem. And it says if you have a continuous function, continuous between your endpoints A and B, you really don't care what happens outside of A and B because that's not important to you. But if you have a continuous function, then there is some point C between your endpoints A and B so that the average value of the function is exactly equal to the function at that point. So in other words, in the picture here, for instance here, this C is what I'm talking about. So another way to say saying this is at some point we are average. Now the main topic of what we did last time was finding volume. Now we already knew how to find volume. The way you find volume, or at least one way to find volume, is you break it up into small pieces. And in particular, we think of it as taking slices. So we're slicing up our volume into small pieces. Now, here we're talking about a specific kind of volume where we take a volume of revolution. The picture is really massively terrible. People who write calculus books hire the professionals to draw these pictures. So the idea is you have a function on top, and you have a function on the bottom, and you're going between 2 points. So you have a region defined by these things. So you have this region, and what you're going to do is you're going to rotate it around some axis. In this case, I've drawn it so you rotate it around the x-axis. Now, you don't have to rotate it around the x-axis. You can rotate it around anything you want. You can rotate it around the line x equals 1, x equals -5. You can rotate it around a slanted line, y equals x. You can rotate it around the y-axis. Anything is, you can do all sorts of things. But basically, we're only going to focus on just two very basic cases in this class. Namely, when we rotate around the x-axis, and we'll also talk about when we rotate around the y-axis. All right. So what happens? Well, we take this region here. It's two-dimensional, and we just spin it as if this were the center. So we always keep the same distance, and we just go and spin it out. And as it goes around, making a full circle around, it sweeps out a three-dimensional shape. And our question is, how big is that shape? And of course, it depends upon what our area is, the region we started with. So for instance, by taking the top half of a circle and spinning it around the x-axis, we found that the volume of a sphere, because that's what you get when you take a circle and you spin it around the axis, you get a sphere. So we found the volume of a sphere is 4/3 pi r cubed. And in general, what you're going to get is you're going to get some strange shape. And how do you think of the shape? Well, you think of it as taking a slice. So in this case, we take a slice here, and we see what does it correspond to. Well, if you take a slice three-dimensionally, what you basically get is a shape that looks like this, an annulus, or, as most people like to call this, a washer. So a washer is essentially a big circle with a little tiny circle in the middle punched out. And then you get a little bit of a thickness. Now, this thickness here corresponds to this thickness there. So this corresponds to this little thickness here. So what's the volume of this shape? Well, the volume is very simple. I just take the area. Well, the area here is a big area of a big circle minus the area of a little circle. So the area of the big circle, well, that's pi times the big radius squared, or you think of the big radius as being the distance furthest out. So in this case, it's f of x minus pi times the little radius squared, or g of x. So pi f of x squared minus pi g of x squared, that's the area of the circle. Then I times it by the width of this washer, or I should say really the height, dx. This part right here, that is essentially the volume of a single washer. But we don't want the volume of just one of them. We want the volume of all of them put together. So what do? We add them up. And that's what that notation means. Whenever we see an integration, just think of it as you're adding stuff up. And in this case, we're adding up the volumes of these washers. Then remember, the integral sign is essentially just the letter S stretched out. S is for sum. It's adding stuff up. So from A to B. Okay. Another way to think about this, by the way, f of x, you can think of this as your outer radius. So you take your outer radius squared minus your inner radius. G of x is your inner radius squared. So the outer radius is from where you're rotating around to the outside edge. In this case, the function that's highest up. And the inner radius is where you're rotating around to the inside edge, which is g of x. Oftentimes, when you think of it in terms of this, it's really easy to remember the formula. If you just remember pi f of x squared minus g of x squared dx, then it's not always clear, what was that f of x meaning? Why did we do that? But if you think of it as pi, oh, the big radius squared minus the inner radius squared, and then you say, oh, okay, f of x was the big radius, g of x was the small radius. It's a little bit easier to remember for some people. All right. So let's see. We should probably do some examples. So let's try a very simple one. Let's take y equals x squared. And let's go from 0 to 3. And I just want to go from y equals x squared down to the x-axis between 0 and 3. So I want to take this as my region. And let's do the case where I revolve around the x-axis. How do we find this? Well, very simple. We have a formula. Namely, we have this formula that tells us that the volume is the integral where we have these various things. So we just plug stuff in. So in our case here, we have that the volume is pi times the integral. And I'm integrating using this formula. So I'm integrating with respect to x. So the way I'm thinking of it is I'm taking small slices. So I'm making these little rectangles and I'm spinning them around. So my widths are dx widths. And then I say, okay, what's the top function, the outer radius? It's the function x squared. So I'm going to take x squared squared. So don't forget you need to square it. It's really easy to forget to take the function squared. What's the inner radius in this case? Well, in this case, the inner radius is 0. In this case, also, it's referred to as just the disk method. So a disk is essentially a washer without a hole. All right. So, and finally, what are the bounds? 0 and 3. Because we're going from 0 to 3, as I said right here. Now it's really simple. We clean it up. X to the fourth dx. And this is one of our really happy integrals. This, in fact, is one that we'll see most often, x to the power. So this is the one we know by heart. So this is 1/5 pi x to the 5th evaluated from 0 to 3. So that's 1/5 times pi times 3 to the 5th. And 3 to the 5th is? That's right. It's 243. Good. And there we go. So 1/5 pi times 243. All right, that was pretty simple. Let's shake things up a little bit. Suppose now, instead of taking this region and integrating as I go around the x-axis, what if I said, well, what happens if I spin it this way? So previously, I really should have drawn the three-dimensional picture. So previously, I had this region, and when I spin around the x-axis, I come down here, and I make something that looks roughly like this, more or less. Now I'm taking that same region, but I'm spinning it around a different axis. So I'm taking the same region, but spinning it this way, and so the shape I'm going to get is going to be a different shape. So it looks like, if you were to think about it, it's a cylinder which has sort of had something scooped out of it. This, what we would call a paraboloid, scooped out of it. Now, if we go back here, there's really nothing special about what we did with integrating with respect to x. And in general, if you remember last time when I talked about the formula, I didn't say dx, I said d dot. Whatever it is you're integrating with respect to. Because if you just tie yourself with respect to x, you might miss out on seeing how to do the integral in a different way. So I can do the exact same thing, where what I do now is I take slices, but now instead of integrating with respect to x, I take my slices this way. I integrate with respect to y, so that if I look at what a typical little thing does, well, lo and behold, it does the exact same basic thing. It makes a washer. Okay? So that we'll go through, we'll plug in the formula. So the volume is pi. And now what we have to do is figure out how everything changes. So let's come over and work with this a little bit. If here I go from 0 to 3, where does y go between? In other words, what is this value up here at the top? It goes from 0 to 9. Because y is x squared. So if x is 3 here, then y is 9 over here. All right. Now, this line here, I can think of this as a function. What does this line correspond to if I were to go straight up and down? We have a name for this line. X equals 3. This is the line x equals 3. Right there. Finally, this function y equals x squared, well, I know what y is as a function of x, but I can also write this line x as a function of y. So if y equals x squared, x is square root of y. Now you might say, well, shouldn't it be x is plus or minus the square root of y? It's true. If y equals x squared, x equals plus or minus the square root of y. But x equals minus the square root of y is this other side of the parabola. So there's the x equals square root of y is this side, x equals negative square root of y is this side. I want to stay on this side, because I'm really interested in this curve here. So this is my region I'm going to be rotating around. So we go through and we figure out the bounds. So where does my slice go between? Well, it goes from my y values. My lowest y value is 0. Highest one is 9. All right, that's easy. Then I'm going to have something squared minus something squared dy. Now, what comes here? Well, that's the outer radius. So the outer radius is where I go from. I take where I'm revolving around, which is the y-axis, and I go out to the outside part. In that case, it's this line here. And I say, what is this distance as a function of y? In this case, what is that distance? 3. It's always 3. It's fixed. It's the function x equals 3. The inner radius is the length from where I'm revolving around to where will be the inside part of the washer. So what is this length as a function of y? Square root of y. So it's going to be 3 squared minus the square root of y squared from 0 to 9. Setting up is most of the hard part. Now it's very simple. So we have 9 minus y dy. We can integrate 9y minus a half y squared. evaluated from 0 to 9. Very lucky for us. When we plug in 0, we get 0. So really, we just need to plug in 9. So that's pi 81 minus a half times 81, or 81 over 2 pi. OK. Let's try something else. So we just saw that I can rotate with respect to y. I should say rotate around the y-axis. And it's very simple. I just sit down. I figure out what my inner function is as a function of y. I figure out what my outer function is as a function of y. I figure out my bounds. And it's just the same exact formula. Well, suppose I ask for something more interesting. Here's a function of y. The function y equals x minus x to the 12th. Goes from 0 and 1, and you can check at x equals 0, I get 0. And at x equals 1, I get 1. And it looks something like this. And I can say, well, look, I'm going to take the curve, or I should say the region, that's below the y equals x minus x to the 12th curve, and above the x-axis. And I want to figure out what happens to this volume if I rotate it around the y-axis. Now, if we rotate it around the x-axis, it's not very interesting, because we already know what happens. We take pi, this function squared. We get some weird numbers, but no problem. But I want to figure out what happens when I rotate it around the y-axis. Now, how can we do it? Well, if I think about it, what do I need to do? There's a few things I need to do. First off, I have to figure out what this height is. If I know what that height is, then I know what my bounds are. I go from 0 to wherever this is. And I can figure out that height. That's not hard. Because what I do, I take the derivative, set the derivative equal to 0, and solve. You'd get some number. It's something like the 11th root of 12, 1/12, something like that. Ugh. I'm already not liking this. But it gets worse. What else do we have to figure out? We have to figure out some function for this length, which will be the outer radius. And we'd also have to figure out some function for this length, which would be the inner radius, which means that we'd really have to solve for x as a function of y instead of y as a function of x. Now, how do you solve for y as a function of x? Sorry, x as a function of y, given this? Well, good luck. Hope that's not on the final. You can't do it. But I really want that number. I really want to know what it is. OK. Well, then we're going to have to come up with something new. Because our old trick, where we just use washers, there's no way it's going to cut it. I'm never going to find that. OK. So let's think about what I can do differently. So what can I do differently? Well, I start with my region, and I think about what was I doing before. Previously, what I was doing before was essentially, if I were trying to use the washer method with this problem, I would be thinking of essentially taking a small little rectangle and spinning it around. I'd be integrating with respect to y. Well, that's just one way to split up a volume. If I'm looking for a volume, I can figure out a different way to split it for volume. I say, well, OK, here's what I'm going to do. Instead of taking these kind of things and spinning it around and get something out, I probably should give myself slightly more space. So I'm going to take this region and spin it around. So we'll get, yeah, definitely should have planned ahead. OK. So instead of just taking a horizontal slice, I'm going to figure out what happens if I take something like this and I spin it around. I'm going to get a different kind of shape. I'm not going to get a washer. What am I going to get? Well, if I spin it around, and if I was a much better artist, two things. At least I can spin it around. I don't know if I can be a much better artist. You'll see you get a different kind of shape. You get something that looks like that. So now what I can do is I can think of, well, I'm going to do something else. I'm not going to split my volume up as a bunch of washers and then add them up. I'm going to split it up things that look like this. If I can figure out how to find the volume of something that looks like this, and I just split up into things like it, then I'll have my volume. Now, this kind of shape we call a shell. So as before, we were finding volume, we were doing what's called the washer method. This is a way of finding volume called the shell method. So what's our first step? Well, the first step is we have to think about how big is the shell. So I need to find the volume of a single individual shell. That's what we did over here. When we started with our washer, we said, well, what's the volume of the washer? Well, we find the volume of the washer, and then we say, okay, here's the volume of a single individual washer. And then we add them up. So once we find the volume of a single individual shell, then we're going to be peachy. Excuse me. All right, so how do we do it? Well, we're going to do a trick we've done a couple of times. Where we, pull out our scissors, and we start cutting. Okay? So I'm just cutting my shell on the side. That's not blood. It's not hurt. Don't worry. Okay. After I've cut my shell, I'm going to just open it up and lay it flat. So I take my shell, I cut it on the side, and then I open it up, lay it flat. Looks something like that. More or less. Now, the shell, maybe I don't know exactly what the volume is for that, but this I can figure out what the volume is pretty easily after I lay it flat. So let's go through and figure out what everything will be. First off, there's a little tiny height here. Now, that height comes from essentially this length here, the thickness. How thick is this? Well, what do we usually call this length? That's our small change. That's our dx. So the height there is simply dx. What about, let's say, this length here? This length corresponds to this length here. Well, in general, if this is my curve y equals f of x, then the length is simply just the height of the function. So this would be my function f of x. Or, if you like, let's just call this the height. So this height here. And finally, what is this length? Well, that's the length if we go around. Or if you like, that's the circumference of the circle. How do you find circumference of a circle? 2 pi times the radius. I'll just write out the word radius here for a second. Now, let's think about what is the radius. The radius is the distance from the center. So I'm revolving around the y-axis. So what is the distance from the center over to this point here? Well, it's the distance we call x, 2 pi x. So that the volume of a single shell will be 2 pi, and we'll first off write out notationally radius times height times small change, d dot whatever. That's your thickness. Or in general, for the more specific case, 2 pi x f of x dx. That's the volume of one of them. How do we find the total volume? We integrate. We add them all up. Once you have the volume of one, to find the volume of all, you add everything up. So now, before, what looked like an impossible problem maybe is not so impossible. In fact, maybe it's possible now using a different technique. So let's see, what did we have before? So previously, we had this function. Our function now, in this case, is the function x minus x to the 12th. And then our bounds are from 0 to 1. Now, what do a and b correspond to in this picture? I should say a and b are basically here and here. So the volume that we want will be the integral from 0 to 1, 2 pi x. And that's just always there for the shell method. times the function f of x, which is x minus x to the 12th dx. Now, whereas before, if we try to use the washer method, we'd have to solve for all these complicated things. We'd have to find that the 11th root of a 12th. I don't know how I would do that. We don't have any of those problems. So I can multiply the x through. That becomes x squared minus x to the 13th. And we're still integrating from 0 to 1 dx. And now it's a simple integral. 1/3 x cubed minus 1/14 x to the 14th, evaluated from 0 to 1. And when we plug in 1, we get a 1/3 minus a 14th. And when we plug in 0, we get 0. So 3 times 14 is 42. So 42 is our common denominator. So this is 2 pi times 14 minus 3 over 42, which we can make that look a little bit nicer. That is 11 divided by 21 pi. Okay. Did I make a mistake? 0 to 1, because we start, essentially now our idea is we're taking these little tiny slices here. So where do we start taking slices? Well, because our integral, our problem, if you come over here, says I want the region from 0 to 1 and below the curve x minus x to 12. So I'm just starting with at 0, and I'm starting to take these little slices here. And I say, what happens to a typical slice when I spin it around? Well, that's the shell. So we find the typical slice, and we integrate. And then we say, well, where did we start taking our slices? Well, that's our lower bound. Where we stop taking our slices, that's our upper bound. A to B, 0 to 1. Okay, so the moral of this story here is that some things which might look impossible using one technique, either washer or shell, are possible using a different technique. So if we had been able to go through and actually figure out what goes on there, we would have gotten the exact same answer. That is an interesting idea. Okay. Let's just check. We should get the same answer if we use either technique. Well, let's do something we can actually do. Because I claim we get the same answer. So you should know both techniques. So for instance, remember we talked about taking this region under y equals x squared from 0 to 3 and rotating it around the y-axis. We already talked about doing that before. Okay. Something like that. So what's the volume? Well, we already know what the answer should be. We should get 81 pi over 2. Maybe we can't see all that. But we figured it out. Let's do it using the different technique that we just learned. So if we use the shell method, then we get that the volume will be equal to 2 pi. And the 2 pi is a constant, so we might as well bring that out. The integral from a to b, and now I'm integrating with respect to x. So instead of 0 to 3, where I integrate with respect to y, I can do 0 to 9. And then what do we integrate? Well, we integrate x, which is our radius, times our height, which is x squared. Okay? So this is 2 pi, integral 0 to 3, x cubed dx. This is 2 pi, 1/4 x to the 4th, evaluated from 0 to 3. And, of course, 2 pi times a 4th, that's like a half pi. And 3 to the 4th is 81. And then if I subtract 0. So I still end up with 81 pi divided by 2. So using the same, well, I can find the same volume in two different ways. Occasionally, though, as in this example, one technique is clearly far superior to the other technique. So let me see if I can draw a picture of this I should say something about a slightly more general version of this formula. Just slightly. So that is, here I just looked at what happens if I go to a single function f of x and I just go down straight to the x-axis. I can still do the same thing where I have a function on top and a function on bottom. And I go from A to B. And then I say, what happens when I rotate this around the x-axis? Well, in this case, if you just think about where everything came from, it's going to be the integral from A to B. Then we still have the 2 pi. The radius is still the distance. So if I'm thinking about taking a small, thin slice here, the radius is still the distance to where we spin around. So in that case, it's x. And then I say, what's the last part? Well, the last part is the height of what we spin around. So the height is simply the height of this little piece here. So what is this height? It's the function f of x minus g of x. It's the difference between them. And then dx. When you recognize where each piece comes from, the x, the f of x, then it's easy to say, OK, how can I modify it to get what I want? So in this case, if I'm looking for volume, I can do 2 pi x f of x minus g of x dx. Now, OK, let's see. Is there anything else important for us to talk about? All right. So I think I said most of what I wanted to say. So our last thing of the quarter here that we talked about, let me just summarize. We have volume. So one way we can find volume, of course, is to take things and break them up. And really, for us, that's the best way. That's what integration is. You break things into small parts, and you add them up. And there are 2 techniques. One technique is you have washers. And you take your washers, and you rotate them around. And using that, you'll find your volume. And the other technique is you break things up into shells. And again, similar idea. Shells are, you think of taking a small slice, and you spin it around, and you see what volume it makes. And thus, you broke your volume up into small pieces, again, shells. And you can find the same volume using 2 different techniques. And that's a useful idea for the final. I recommend that you ponder on that and master that idea. That may not be what I do, but there's definitely something about volumes on there. And definitely something about volumes of revolutions. So I should point this out. If I wanted to find a region, suppose let's do y equals x squared. And here I do y equals square root of x. Suppose I want to see what happens with this region when I spin it around the x-axis. Well, first off, note that I can think of both these curves in 2 different ways. For instance, y equals square root of x is the same as saying x equals y squared. Y equals x squared, which is this curve, is the same as x equals square root of y. And then I can say, well, I know where they intersect. Namely, they intersect at 1, 1. So to walk through this, how do I figure out how to set up my integral? Suppose I want to integrate with respect to x, the volume. Well, I think about, OK, if I'm integrating with respect to x, I really am thinking of starting with a small x slice. And I say, what happens if I were to take this small slice and spin it around? What kind of shape would it make? Would it make a washer or a shell? It would make a washer. That tells me I'm using the washer method. And the washer method says, well, OK, you take the pi, and then you integrate it from your bounds, 0 to 1. And you take the outer function minus the inner function. And you say, OK, what's the outer function? Well, the outer function is from where you go from your rotation. You're rotating from the x-axis to the top. So in this case, it's the square root of x is the outer function. And the inner function is from where you're rotating, the x-axis, to there, which is x squared. So by thinking about, okay, what kind of shape do I make if I try to spin a small, thin strip around? Then you figure out, okay, I'm supposed to use the washer method. On the other hand, you could say, well, look, maybe I don't want to integrate with respect to x. Maybe what I want to do is I want to integrate with respect to y. So you say, okay, well, think about what happens here. If I take a small strip with respect to y and I spin that around the axis, what kind of shape do I make? You make a shell. And you say, okay, now I'm in the shell method. And I remember the shell method, there's a formula for it. It's 2 pi. And then the next part is you say, well, the next part is the radius. So now instead of integrating with respect to x, I'm integrating with respect to y. So I think, well, what's this distance here? Well, it's really the length here. What is that? It's the distance is simply how far up I am, which is y. And then what's the other part I need? The other part I need is the height. And in this case, the height of the shell is this length here. So what is that length? Well, I take the right minus the left. High value minus low value. So what is the high value? Square root of y. What is the low value? Y squared. So you would take the square root of y minus y squared. And notice that these don't get squared. These do. So you have to make sure you don't mix your methods together. And what are our bounds going to be? Well, we start taking slices at 0, take slices up, and then when I say take slices, you imagine you take your slices, spin around, and get your shells. So we start making shells at 0, we stop making shells at 1. So lo and behold, if you go through and you work both these integrals out, you'll get the exact same value. All right. So that's pretty much it for calculus for this quarter. Amazing. You survived. Well, almost. You still have another test. I want to talk a little bit about why you took this class. Now, some of you maybe took this class because you said, I want to be a math major, which is great because we need more math majors in the world. It's a great thing to be a math major. Of course, there are a lot of you, and if I were to guess, I would probably guess that less than half of you are going to become math majors. Maybe even a lot less than half. Does that mean that the people who don't become math majors got nothing out of this class? I hope not. So why is taking a math class important? Taking a math class is important because what you learn in this class is you learn how to do problems. And you may not have math problems in your future careers, but I can guarantee you are definitely going to have problems. And you're going to have stuff that you need to solve. And this is a great chance for you to learn critical thinking skills, logical thinking skills. How do you think through a problem? I mean, how did we do problems in this class? We sat down and we said, well, we have these really hard problems. How do you measure how fast something is going? How do you find the total of something? We said, okay, these are big problems. Let's break them into smaller parts. Work on each part and find the total. And we were able to find great methods that work and useful things. So I think this math class and all math classes in general are really great because you learn how to solve problems. There's a professor who once told me there's a guaranteed method to solving a problem. 2 steps. Step 1, you try something. Step 2, if it doesn't work, try something else. And then, of course, but never give up. I like that technique. Of course, you might get stuck in an infinite loop, which is a bad thing. There's a great Danish mathematician / poet / inventor / architect, great all-around guy, Piet Hein. Did all sorts of cool stuff. For example, here in my hand, I have a small metal object he created. It's called the super egg. Now, this has no flat edge. So if I were to place it on this table, if it's not flat, of course, what should happen is it should fall on its side and roll away. But here's the amazing thing. It doesn't fall over. It's balancing on a single point. You don't think it should do that. There's no trick, no magnets, no wires. See? How does it work? It's simple math. If it starts to fall over, the center of gravity pulls it back. Now, Pia Hein, as I said, he was many things. He also wrote what are called grooks, which are really short sayings. And so I want to leave, at the end of this quarter, 2 grooks, and then we'll start a review session. The road to wisdom. Well, it's plain and simple to express. Err and err and err again, but less and less and less. It's also the secret to passing calculus. Everybody makes mistakes in calculus. When I took calculus for the first time, I made tons of mistakes. You learn from your mistakes. You are going to make in your life incredibly boneheaded, stupid mistakes. I can guarantee it. And if you don't, you're not living a very interesting life. But learn from your mistakes. And you learn from your mistakes and you get better. And you make smaller mistakes and you get better. And you get better. It's a process. And the other thing I like, problems worthy of attack prove their worth by fighting back. Don't be intimidated by hard problems. Excuse me. You are going to have hard problems in your life, but you'll be able to solve them. You are good students. Regardless of what you got on the midterms, I think you're all very smart people. And I like all of you. I hope you all have success. So I want you to go on, have great lives, relax. Don't worry about this final. It's just a stupid test. And that's it for our class. So thank you.